So, do you remember from last week, looking, and maybe from your test today, the levels of structural organization? What was our first one? Chemical, right? Chemistry. So that's why we are incorporating that into our A&P material, even though it probably feels like, well, why do we have to know this? All of the things happening in your cells are happening in through chemical reactions. So when we think about chemistry, and how many of you have had chemistry? I'm assuming everybody, right? At some point. What's that?
I'm in it right
You're in it
now.
now? Awesome. So you probably have to know all the elements, right? Oh, okay. Fair enough.
Yeah, I have to learn like 30 by like Friday.
Awesome. You can do it. Well, if you want to use that cake, take a picture, whatever. But chemistry, when we're talking about kind of what is it, chemistry is kind of divided into matter and energy. And matter is kind of the stuff. Everything is made of matter. And then energy is kind of putting that matter into motion. And energy is this funny thing because it's not tangible. You can't really see it, but it's there. And energy, we also say, is neither created nor destroyed, but it's rather sort of redistributed. So, for example, if I were to take this eraser and throw it across the room, and which was really impressive, I know. When I threw it, I was using energy, albeit not much, to propel it in the air, but then the eraser ends up having energy within it as it's moving, some kinetic energy, and then once it hits the floor, the energy stored up in it kind of lets it bounce away again. So what I'm trying to get at is that with energy, we have potential energy, we have kinetic energy, and basically what that refers to is kinetic energy is kind of the movement. Where are my markers? Let's see. I know this isn't written on the slide right now, but I'll show that to you in a second. So kinetic energy is basically sort of the mechanical, the movement. So if you think about the air right now, it's about 78% nitrogen, about 21% oxygen. Those gas molecules have kinetic energy and they're moving all over the place. You can't see it, you can't feel it, but it's there. But the sort of stored up energy that allows it to work is called potential energy. So that's going to be kind of our stored energy. Does anyone know the name for the energy currency of the body, of our cells? We typically use its 3-letter acronym. ATP, exactly. So ATP is basically a form of potential energy, and when ATP is broken, the energy harnessed in those bonds provides the ability to do work, for example. So your muscles, when those contract, require ATP to actually contract. So we'll talk a little bit more about forms of energy in a bit, but this slide is looking at elements. So whether you're looking at, there's a periodic table right there on the side of the room, or the groom's cake that I had up, there are, I want to say, 118 elements, and we know about, I feel like it's always changing. There's some unknown elements, but essentially of those 118, each one of those, an element is basically a substance composed of the same types of atoms, and they can't be broken down into simpler substances. So what that means, the element carbon is made up of carbon atoms. The element oxygen is made up of oxygen atoms, and so on and so forth. And so when we're looking at this slide, this is looking at basically the 6 most abundant elements that comprise almost every living thing, and mostly the top 4. So carbon, hydrogen, oxygen, nitrogen are kind of make up 96% of cells, and then phosphorus and sulfur are found as sort of I don't want to say satellites, but they're found in lesser amounts. So the chemical, when we're looking at the periodic table, the chemical symbol of an element is represented by 1 or 2 letters. You know, those, again, you're not going to have to memorize it. I mean, some of them I'm going to be using interchangeably, like these. So the ones that we use a lot, you're not going to have to memorize the whole periodic table. Audubon sounds like you might have to for your class, but you'll be one step ahead of the game. So when we look then at the periodic table, there's a number that is typically written to either on top of the number, on top of and to the side of the number. If you look at the second page of the worksheet I gave you, this is representing atomic number 5. So the atomic number of an element represents the number of protons in that element. Do you remember what charge a proton has? Positive, exactly. Let's see. And then the number of neutrons is going to be relatively similar to the number of protons. Do you remember what charge neutrons have? Neutral, exactly. So, and then electrons, what charge do those have? Negative, exactly. So when we're looking at these numbers here, we're going to see that the number of protons will always equal the number of electrons. And what that means is that atoms on a whole are then neutrally charged if your positive charge is equal to your negative charge. And then if atoms lose or gain electrons, that's referred to as forming ions, which we'll get to in a minute too. So basically, number of protons is your atomic number. Let me write that up here. So your atomic number equals the number of protons. And then your atomic, there's a couple of names for another term. There's atomic mass, the atomic mass number. The mass number would equal the number of protons and neutrons together. So we'll go through that a bit as we look at this. Looks like a little bit later. But before we do that, it looks like this slide kind of got shuffled around here, but we can talk about it here. I'm going to go back to forms of energy, and then we'll go back into the atom. But forms of energy, so remember energy is kind of putting that matter into motion. But what we're referring to here is, so we have 4 different sort of forms of energy. The first being chemical, and chemical energy is kind of like the energy that's stored up, that potential energy in the bonds of different molecules. Electrical energy is going to represent the movement of charged particles. So not only does it represent like the electrical energy to power the lights in this room, but also if we think about ions that cross cell membranes, for example, that produces electrical energy. What about mechanical energy? Any ideas about what that might be? From a physiological standpoint?
Is that the movement of the body?
Exactly, yeah. When we think about something like muscle contraction, for example. So with mechanical energy might be chewing. So the actual motion of chewing, and then chemical energy would be breaking the bonds in the food that you're chewing. So as the enzymes and things play a role in breaking down those food particles, then that will give you energy. And then radiant energy represents different types of, think like X-rays or the visible rays. We have there's a certain wavelength spectrum that we can visibly see. That would represent radiant energy. Ultraviolet light will help to synthesize vitamin D in your skin, so that's an example of radiant energy as well. So each one of these represents a form of energy. And it, like I said before, it's weird because it's not really like a tangible idea, energy. It's just this thing that helps power everything that we do. So if we go back to the atom, I know we just kind of talked about this, and I don't know why these slides got shuffled, but when we're looking at the atom, the protons and the neutrons are in the nucleus of the atom, and then the electrons will orbit the outside. Depending on the different element, that will kind of dictate how many protons and electrons they have, and the electrons in the outermost shell, if you picture, and this one is a little bit tricky to see because it's showing all these kind of orbits, but each picture like a kind of like a ring around, or concentric rings around the nucleus, and that's where the electrons will occupy and orbit. And the outermost shell, those electrons are sort of available, if you will, to bind with other atoms. Does anyone remember what the outermost shell of an electron or of an atom is called?
Balance.
Yeah, exactly, the valence shell. And so that is going to, those electrons will be able to interact with other electrons and other atoms. Isn't the covering on a window sometimes called the valence?
Isn't it something that you?
I think so. So outer, I don't know, you guys are gonna start seeing A and P everywhere, right? You're welcome. So, outer window, outer shell, I don't know if that helps. And I kind of mentioned this one too, and I wanna make sure, are your slides the same as what I'm showing up here? They should be. Okay, good. Okay, that happened last week about this time, so I'm gonna have to investigate that. I'm not sure.
It's like a mechanical room next door.
Oh, is there?
Yeah.
I was hearing music during the test.
Yeah.
So.
I know.
But there's like it's like an office or something.
Yeah, there must be. I know the EMT storage and teaching is down here, as well as the kitchens, so who knows. When we're looking at different elements, so again, think about the cake in your head or the table on the side of the room here, there are 118 different elements, and every element is just made up of atoms. And so, and atoms have the same same components. Atoms always have protons, electrons, and neutrons. So that said, how do we tell the difference between atoms? And that's by the fact that they have different amounts of these materials. So I think I mentioned to you last week structure equals function, right? Did I go a little nutty about that? So essentially, if we're changing the structure, we're changing the number of protons, then we're going to change the function and change the entire element. So, and here's the slide that has those terms on here. So the atomic number, again, is the number of protons and also electrons within an element. So for example, this is showing sodium here, and sodium has 11 protons, and therefore it also has 11 electrons. The mass number, which is also known as the atomic mass or the atomic mass number, is going to be equal to the number of protons plus the number of neutrons. And the reason why we don't include the number of electrons, I thought that was going to make it easier to read. The reason why we don't include the number of electrons is because the number of the mass of an electron is so teeny tiny small that it doesn't really contribute to the overall mass of the element. So if the mass number is equal to the protons plus the neutrons, and I'm telling you that sodium has a mass number of 23, how many neutrons would it have? You have to do a little math. So the mass number is equal to the protons plus the neutrons. So here, let me write this out. Maybe that would help. If I can find my, here. Oh, just walking around. Okay. So the mass number is equal to the number of protons plus the number of neutrons. And I'm telling you that our mass number is 23. And then how many protons do we have? 11, right? So 11 plus n, if we were to solve for n, then how many neutrons do we have? 12, yeah. Does that make sense why it's not 1?
Yeah, I was thinking that it was electrons, then it was just like the extra number. I
Oh,
know that there was
I
3
see.
numbers.
Right,
so
right.
that's where I was going.
And I'm actually glad you brought that up because with the number of electrons, this picture also shows the different orbitals. And without getting into too much chemistry detail, there is a very specific way that electrons can orbit the nucleus. There can only be 2 in this immediate shell, and then every subsequent level can only have 8. So sodium has a total of 11 electrons. So there's 2 here, there's 8 here, so then there's 1 extra that's kind of floating on the outside. That is very unstable for an atom. I don't want to personify these too much, but they don't want that. Sodium wants to get rid of that electron because that makes it very reactive. Basically, the elements and atoms want to occupy, they want all of those electron levels occupied, and it's sodium having that extra electron, it's not going to pick up 7 electrons, but rather it just kind of wants to get rid of that. And so sodium will form ions pretty frequently. So this kind of leads us into the next sort of mini topic of looking at how atoms will bind and bond with each other. Just checking our time here. So we have 2 major types of bonding, ionic and covalent. And with ionic bonds, which is the one on the right here, electrons are transferred from one atom to the other. I'm going to type that in here. So with ionic bonds, electrons are transferred, and that's not.
Is each layer of the atom a valence shell where those electrons are?
Good question. Each layer of the atom is what we refer to as an electron level or an electron shell, but just the outermost one is the valence.
Oh, okay.
And that valence shell is what reacts with nearby atoms. So if we look at the picture from the previous slide, just this outermost circle, if you will, is the valence, and there's this 1 electron out there, so that wants to react with other elements. Does that make sense?
Mm-hmm.
Is everybody else following me too?
So if they would get rid of that 1, then would that just second one become the valence shell?
Exactly, yeah.
Okay.
And it would then it would be more stable and, happier, so. And that's, so sodium as it naturally occurs, sodium is a metal, and if you drop it in water, it's extremely reactive. But the way that we know sodium, like sodium chloride is table salt. Sodium by itself is a metal, a reactive metal. Chlorine by itself is a poisonous gas. But you put them together and you can eat it, and copious amounts if you're like me. So, hi. Another example of structure equals function, where if you change the properties by losing or gaining electrons, that's going to greatly impact the actual atom itself. And so the way that, let's see.
Because it only has 1 in the outer shell, does that mean that it's looking for 7 more? Like,
Good question. I would say because of the way electrons are transferred and sort of how bonds are formed, it's more likely to want to just get rid of it rather than, it would be easier for the atom to lose that electron and then have a stable next shell level than to gain 7 more. On the other hand, chlorine, I don't know if I have a picture of that, like with sodium chloride, has, let's just pull this up really quick, atomic structure. So if I can get this to just, okay. So here's chlorine, And if you count it up, it has 17 electrons, so there's only 7 in that outer shell, which is kind of hard to see here, which means it kind of needs one more electron to feel stable. And so that's why sodium chloride, oh look, we can buy this photo. I don't really want to do that. Anyway, chlorine is going to pick up that electron from sodium, and sodium is going to give its extra electron away. It's not really an extra electron, it's just orbiting that outside, kind of like a lonely rider out in that electron shell wants to get rid of it.
Just get rid of it means like they join, right?
Yes, I keep saying get rid of it,
I picture them being separate.
but it actually, it's sort of, this picture it kind of shows what's happening. So with this picture on the right, imagine that the top, is that right? Yeah. This top picture here represents sodium. So it's got this extra electron hanging around, and it's going to transfer that electron to chlorine, who's going to pick it up essentially and bind with it, and then that will become negative. So, it's interesting because with ionic bonding, the atoms do end up completely transferring those rather than just and that does kind of form the bond. It's kind of a strange interaction. Whereas with covalent bonds, the electrons are shared and they kind of just orbit around each other. I don't know if I'm explaining this very well. With ionic bonds, sodium is going to completely transfer that electron, and chlorine is going to completely pick it up, which will then change the properties of the atoms themselves. And so maybe that would make more sense if I explain that. The atom that ends up, or both atoms with an ionic bond will end up either losing electrons or gaining electrons. So it's sort of like one atom's trash is another atom's treasure, right? So I don't want this electron anymore, but chlorine's like, I do, so I'll take it. But one of those electrons, and there's tons of different ionic compounds, I'm just using sodium chloride as an example, but sodium will end up losing its electron. So if a particle is losing negative charge, is it becoming more negative or positive? If it's losing negative charge. Positive, exactly, which is kind of a weird concept to wrap your head around. So then the atom that ends up losing its electrons becomes positively charged, and we call that a cation. And one way that I've always remembered that is that the T in cation looks like a plus sign, right? So it's positively charged. The other atom that picked up that electron, if an atom is gaining negative charge, then does it become more positive or negative? Negative, exactly. So, and those are called anions. So in the example of sodium chloride, sodium loses the electron and becomes a cation, and then chlorine picks it up and becomes an anion. And then you've probably always heard the expression opposites attract. So when you have a positive charge and a negative charge, those attract. And so that attraction is this sort of transfer, and again, kind of a weird concept to wrap your head around, but that ends up kind of binding it together. But it's kind of a weak bond. So if you think about when you, hopefully this doesn't happen this semester, but let's say you get a sore throat, and I'm not picking on you, but you're coughing right now, so hopefully it's nothing. But if you gargle salt water, sometimes that helps, right? It tastes gross. But what happens when you dump salt in water and maybe stir it up a little bit?
It just dissolves.
Yeah.
Dissipates.
Exactly. It dissolves, it kind of dissipates. And so to the naked eye, it looks like it's just sort of disappearing. But in reality, those ionic compounds like salt, when they get in water, they dissociate, which means they basically break apart. And water is polar, and so the negative charge, the negative part of water will bind with the positive sodium, and then the positive part of water will bind with the negative part of chlorine. So it's, you end up having, instead of it dissolving, it kind of well, it is dissolving, but what's really happening is that you have water molecules kind of hugging these ions. So, let me see. Oh, we only have 2 minutes left. And this is exactly the picture I was looking for with that. But when that happens, ions can also be, this will be our last slide here, are also referred to as electrolytes. And electrolytes are just substances that will conduct current in solution, like an ion. And this is a picture showing, each of these little kind of Mickey Mouse structure things. These are water molecules, and water is polar, so part of it is positively charged and part of it's negatively charged. And so when you put salt in water, those salt molecules end up breaking apart into their ions, and then, so here's our anion chlorine, here's sodium, and they end up binding to the water. I have the pictures here represent, so if you are, the top left shows basically about a 0.9% sodium chloride solution, like an IV drip, and that is, there's a term called isotonic that means it's the same concentration as basically the blood, and so it can be used to replenish fluids. Gatorade is an example of something like if you are trying to replenish fluids after sweating a lot, or with kids that end up getting sick, like a lot of vomiting or diarrhea, you need to replenish those electrolytes because it can be dangerous if you, if your levels of electrolytes are not in balance. That can have severe impacts on the nervous system, on the muscular system, etc. So.
It doesn't mean just salt, does it? I mean,
Right.
is electrolytes like salt? Or is
Yes, we use the word salt, but a salt is
Sodium.
basically an ionic compound that's not an acid or a base. So sodium chloride, in your body you've got calcium phosphates, you've got calcium carbonate, you've got tons of other salts that are not just what we know as salt, right? But in all of those cases, each one of those compounds is an ionic compound that forms those ionic bonds. That is not an acid or a base. So tomorrow, we'll finish the rest of this chemistry stuff tomorrow before we talk about the cell. But there are acids and bases that are also ionic, but behave a little bit differently. So, so I think, let me see here. We will just